Hello and many thanks for watching. My name is F Le Vot. I am a member of the Statistical Physics group of the University of Extremadura in Spain, together with my fellow co-authors Enrique Abad and Santos Bravo Yuste. This work is a collaboration with Professor Ralf Metzler from the University of Potsdam in Germany. The aim of our article is to describe the physics of a diffusing particle dragged by a velocity field in a uniformly growing domain. Both advective contributions play a key role in the underlying reaction-diffusion kinetics. According to Einstein's pioneering work, the Brownian motion is characterized by a mean-squared displacement which grows linearly in the long-time regime. However, a nonlinear MSD is found in many experimental systems. This behavior is called anomalous diffusion. The latter can be subdivided into subdiffusion if the MSD grows with an exponent alpha less than 1, or superdiffusion if it grows with an exponent alpha greater than 1. Subdiffusion is observed in a wide variety of systems and phenomena. For example, intracellular transport, formation of morphogen gradients, charge transport in amorphous semiconductors, or the propagation of cosmic rays in random magnetic fields. Levy flies are a special case of superdiffusion used to model foraging or the propagation of diseases. Relevant diffusive processes take place in domains evolving in time. Concrete examples are found in a biological context, such as expanding cells, developmental tissues, lipid vesicles, or biofilms. Another important example is the expanding universe. In this paper, we only consider the case of a uniform expansion in one spatial dimension. As you see in the figure, the position of each point at a given time is related to their initial position via a time-dependent function, the so-called scale factor. Of the three kinds of diffusive process we have mentioned, Brownian motion, subdiffusion, and Levy flies, subdiffusion is the one in which the transport statistics is most strongly affected by the domain growth. Apart from changing the behavior of the MSD, the domain growth gives rise to a time-dependent kurtosis. This feature doesn't appear in the case of static domains. The change in the kurtosis means that the shape of the particle's probability density function is modified as time goes by. The case of a power law domain growth with exponent gamma equal to 1/2 of alpha stands out because of its interest. In this case, the propagator at short time preserves the characteristic caps of static domains. However, at large times, the propagator evolves towards a Gaussian-like behavior. For other values of gamma, the propagator preserves its caps at long times. This suggests that tuning the domain growth exponent gamma may control the system memory of the early time behavior. In contrast to the domain growth, switching on a velocity field doesn't alter the shape of the probability density function. It is simply obtained from a Galilean shift of the zero field PDF. We find that the fractional diffusion advection equation looks like the Fokker-Plan equation, but with the time derivatives replaced by material derivatives. Therefore, we think that this paper could also be of interest for mathematicians and experts in fluid mechanics. Finally, we studied the mixing properties of two diffusive pulses subject to opposite drift velocities in a growing domain. The domain growth causes a centrifugal drift that hinders particle mixing. For sufficiently fast expansions of the domain, this drift is able to completely stop the reaction-diffusion kinetics. However, for not very fast expansions, the effect of the domain growth is mitigated by the advective motion of the pulses caused by the velocity fields. Thank you for your attention. We hope that you like our article and look forward to any feedback you might have.